Thank you very much for the introduction and for the invitation. I'm very happy to be able to speak at this workshop. We have a bit of pressure because it's the last day, but we try to keep you awake. And the talk is a first part of a 2-lecture series, and Victoria will be building on what I say now in the next talk. So as it was anticipated, what I will be talking to you about today is a specific model of infinity n categories that is called the model of n-complicial sets. And what I'm hoping you get out of this talk is not a precise account and remember all definitions that I will not be giving you. The subject is particularly technical, but I hope you will get a vibe for what an n-complicial set should look like, why it should model an infinity n category, and what are the efforts that Victoria and I and also other mathematicians are making towards understanding better this model. So this is a one-parameter talk in that you can fix your favorite positive integer n, and you can read the talk in 3 different ways, depending on whether n is 0 or 1, 2 or 3 or higher. And what I mean is that when n equals 0 or 1, everything I say will be correct, but less interesting, in the sense that it will be either straightforward or already like classically understood. Whereas the case n equals 2 is interesting, and the things that I would be saying are proven, most of them recently. Whereas we are keeping an eye for higher values of n, but a lot of the steps, while they make sense and we believe are true, have not been proven yet, and some are very hard. So you can keep in mind, keep an eye towards higher n, but for higher n, a lot of things that I will be saying are only conjectured. Okay, so I'm proposing a talk about infinity n categories, and maybe we have a vague idea of what an infinity n category should be, but let's remind it for ourselves. So what we often hear is that an infinity n category X should be something like a category weakly enriched over n-1 categories. And maybe the enriched part is the one that does not scare us too much, in the sense that it will involve higher information. But what it makes this definition particularly hard to grasp, and as a matter of fact, what makes it a guiding principle and not a precise definition, is the fact that there is a lot of interpretation in how to formalize this weakening, the fact that it's only weakly enriched. And what we expect, and we all seem to kind of agree on the type of structure that we expect from an infinity n category, is that it should have some objects that we think of as morphisms of dimension 0, as well as morphisms in every positive dimension that go between morphisms of lower dimension. But then what we request is also that we have some sort of weak composition map for those morphisms in each dimension. So those morphisms should compose weakly, and there is again this word weakly that makes things fuzzy. And moreover, I also want all morphisms that are in high dimension. What do I mean by high dimension? I mean higher than the parameter n, to be weakly invertible. So, and are weakly invertible for k bigger than the fixed parameter n. And since there is a lot of interpretation for these, different mathematicians have interpreted these in different ways, and the interpretation that we're going to follow for today is the one of an n-complicial set, and we will be getting there. So ideally, what I would like is to be able to formalize X as a mathematical object so that I can work with it. But since I want to do homotopy theory with it, it would also be useful to have a supporting theory. And I am a model category person, so in our situation, the supporting homotopy theory will be given by a model structure M. You could probably adapt whatever I say using a different meta theory, and I think it would lead to comparable like difficulty and advantages. So what do I mean? Like, what does a model category do for us in case we are not super familiar with them? A model category consists essentially of a category with a specified class of weak equivalences and also extra classes of maps that I don't want to go into right now. And I want to be able to recognize amongst the objects of M some that will be my infinity n categories. So this M is meant to be an ambient where all the infinity n categories live. And it is convenient to have this supporting structure given by M because it will speed out for me automatically a meaningful notion of mapping spaces that for today I am denoting as map AX. So there are many ways to achieve these derived mapping spaces. They are spaces or n-complexes. It's a well-defined homotopy type. You can realize it using Hammock localizations. You can use like simplicial and co-simplicial resolutions in like one of the two variables. Or if your model structure happens to be simplicial, then you can realize it as a derived HOM. But the point is, I want to think that this space is now the space of X-valued A-shaped diagrams. So this is a space where one object looks like a little diagram valued into my infinity n category X with shape A. Okay, so how would I proceed to identify one definition that works for me and one nice model structure M? And if I look around and think about what could be some good extra requirements that I could put on it, maybe one thing that I really care about is that this theory, which is meant to be about a weakening of the notion of strict n categories, should itself recover the theory of strict n categories. And let me just briefly recall what is an n category, a strict n category. So this one is maybe easier to digest than the infinity n category because this is a precise definition. So let me just write over this one. So a strict n category X is now a category really strictly enriched over n-1 categories, and it's going to have objects, morphisms in each dimension that now compose strictly and that are identities when the dimension passes the critical value of n. Okay, so what do I mean that I want to recover strict n categories? It means that I'm hoping whatever M is to find some good construction that allows me to interpret every n category as an object of M, hopefully even an infinity n category. And why would I care about something like this? And I can see two kind of orthogonal reasons. The first one is that it's a consistency check. We are trying to play with hard and complicated objects. So for our own sanity, it would be better to make sure that they do recover a situation that we understand well. And we could also regard these as maybe a source of examples. But on the other hand, this source of examples is not super interesting by itself because the infinity n categories that would arise in nature very rarely have a strict behavior. So instead, I like better the second motivation, which is I want to use n categories to parameterize interesting spaces. What do I mean by this? So I'm putting myself in the situation where, given any D and N category, I can use this functor F, yet to be identified, to produce FD, which is now an object of M, hopefully an infinity N category. And then I can look at map FD into X, where X is some infinity N category. And this is now going to be an intrinsic space in many situations. So even when D is somehow trivial, so here I wrote some toy values that D could take. I took the category with 1 point, the walk in one morphism, the walk in two morphism, composable one morphisms, and then horizontally and vertically composable two morphisms. But if I map out of this not particularly interesting category, then what I am describing is the space of objects, one morphisms, two morphisms, and composable morphisms in different flavors in a given infinity N category X. And this is something that we do want to have access to. So I have, like, maybe a way to rephrase this is that M, the global structure of M, somehow is able to recognize what is the space of all the given structure in the infinity N category X. And obviously I can use the same trick also to draw more exotic shapes that I care about. So say that I have a pasting scheme that could look like this. Or whatever other pasting scheme you might like. And then when I map out of the corresponding object defined by this guy, then what I get is the space of diagrams of this given shape. Okay, questions so far? Okay, so let's try and find this M. And maybe something that is always wise is to at least try and see what happens if we recycle what is the known theory for low values of N. What are the low values of N in this case? Well, we have 0 and 1. And for both cases, the theory of infinity 0 categories and infinity 1 categories find a very good home in simplicial sets. So maybe we can still hope that M could be taken some, maybe simplicial set itself or some variant of it. And since I have said that I'm hoping to have a good construction that eats an N category and produces a simplicial set, in this case, the natural candidate to consider would be the street nerve. The street nerve is a functor that we are just calling N at the moment that takes an N category and produces a simplicial set. And let me briefly tell you what it does. So if D is an N category, what is ND? ND is a simplicial set. So I would have to tell you what is the set of K simplices for each K. It starts in a particularly easy way. The zero simplices of D are of the nerve of D are just the objects of the category D, and the one simplices are just the one morphisms of the category D. Then as the dimension increases, more complicated things start appearing, because even in dimension 2, maybe our first instinct is that a 2 simplex of the nerve of D should just be a 2 cell in D, but this would not behave well with the simplicial structure. So instead, a 2 simplex in the nerve of D is a 2 morphism in D that moreover has a specified factorization of the target. And I drew for you the picture of what a 3 simplex should look like. And it's again a 3 morphism in the category D, but both the source and the target of these 3 morphisms, which are 2 morphisms, have to be a pasting of a very specific shape. So more generally, I am definitely not going to draw what the K-simplex should look like, but instead what I would like you to remember is that sigma, maybe a K-simplex of the nerve of D, consists of a K-cell of D, but with specified weird boundary conditions. Okay, so we have a famous and well-established construction that is valued in simplicial set and takes as input an n category. Let's see what happens when we try to build a theory of infinity n category using this nerve. And maybe it's not a surprise, but this nerve does recover the usual nerve for one categories and what is sometimes called the street nerve, sorry, the Daskin nerve for two categories. And something else that I should point out is that, of course, since D has only interest in cells up to dimension n, at a given point, all the appearing stuff have to be identities. For instance, if D was a two category, there would be no room for a three morphism there. So this would just be an identity. Okay. So let's see what happens when we try to analyze the maybe less interesting case of n equals 0. Maybe we can observe that X is isomorphic to the nerve of D, and now I'm thinking that D is a 0 category, which is also known as a set. If and only if X has the unique right lifting property with respect to Horn inclusions. I know that this is not standard notation, so I'm just putting a U here to mean unique right lifting property. And here K is all possible values between 0 and n. So this suggests that it maybe makes sense to define an infinity 0 category when X has the not necessarily unique right lifting property with respect to the same class of maps. And here I shouldn't use n because n is a fixed thing, so I'm going to use m. Okay, and you may recognize that a simplicial set defined by this right lifting property is exactly a n-complex. Okay, now that's about it for the case n equals 0, and in that case, indeed, one could take M to be simplicial set with the Kahn-Quillen model structure that for now I'm just denoting like this. And a similar story, although significantly more interesting than this one, but a similar story happens for the case n equals 1. And so I have copied the same pattern, and I'm going to stress what is different. So in the case n equals 1, then X is isomorphic to the nerve of a 1 category if and only if it has the unique right lifting property with respect to Horn inclusions, but now only inner Horn inclusions. So now we are going to have 0 strictly smaller than K, strictly smaller than M. And this is maybe a suggestion of why it's good to define X to be an infinity 1 category if and only if it has the non necessarily unique right lifting property with respect to the same class of maps. And this is the defining property of quasi-categories indeed. Okay, now that we are all excited, we hope that we will be able to continue the pattern to the case n equals 2. But unfortunately, it turns out that there is a significant jump in difficulty in going from n equals 1 to n equals 2. And there are different issues that I could point out to you as a manifestation of why there is this jump in difficulty. This does not disprove necessarily that one could achieve a model structure for infinity two categories on simplicial sets, but at the very least, you will block many of your candidate attempts, let's say. So let me mention a couple of issues. Is there any question? No, okay.
There is a question in the chat.
Sorry?
There is a question in the chat, Martina.
Okay.
Can you see the chat, or maybe
yes.
I read?
No, infinity. So if you don't specify any number, infinity category means infinity one. Whereas infinity zero category sometimes is called infinity groupoid.
Okay, thanks very much.
Yeah.
Great.
Okay, so here are some things that will make your life harder when working with, yeah, also I kept switching between capital and non-capital N, sorry about that. Okay, so here's one issue. One property that maybe you don't realize when you do theory of quasi-categories that you use all over the place is that the nerve from cat to simplicial set is fully faithful. This is no longer true as soon as you jump to higher values of N. So first issue is that the nerve from n cat to simplicial set is not full. So already this prevents you from copying a lot of arguments. And another morally challenging fact is that when you do quasi-categories, if you stare at a simplicial set that happens to be of the form nerve of a category, the simplicial structure of it can completely recognize all the structure that D has as a category. But this is not true when you go in higher dimension. So maybe let me phrase this as saying that the nerve of D doesn't recognize the structure, and to be more precise, the composition law of D. And what do I mean by this? Let me add a small example that maybe clarifies this. Here are, I'm gonna write two different non-degenerate two simplices of the nerve of D that in D have very different meanings, but in the nerve of D don't. So here's one simplex. I have F, G, and H. So these two simplex comes from the fact that in D I have a two cell that goes from a one morphism A to the composite of two one morphisms G and F. And here's another one, F, G, G composite F. And here I just fill it with an equality. So these are two valid two simplices of D. They are both non-degenerate. You might at first look think that the second one is degenerate, but it is not. And this one comes from the fact that in D I can compose stuff, whereas this one doesn't. But the simplicial structure of the nerve of D has no way of recognizing that the two play very different roles. Okay, so if these two issues don't speak to you, you feel free to ignore them and just trust me that things are complicated when you go up a level. Is there a question? Ah, okay, not a question. Okay, so I hope this convinces you that maybe it is worth exploring some enhancement of just the bare category of simplicial sets. And this is a direction that has been pursued already by a variety of people. And the modification that I would like to make is to now consider, rather than just simplicial sets, simplicial sets with marking. So I'm denoting the category of such as MS set. And what type of marking am I using? There are a lot of different markings on a simplicial set that you can find in the literature. And this is one of, I would say, one of the most general ones, because you have marking in every positive dimension. So what does this mean? What is a marked simplicial set for this talk? It's a simplicial set where I have a specified set of simplices that I call marked or sometimes thin, and they all have dimension 1 or higher. And the morphisms in this category are obviously morphisms of simplicial sets that preserve this marking. So the fact that I have changed the ambient category that I'm aiming for also suggests that I should enhance accordingly the nerve construction. And this is what I'm going to be doing now. So we want to consider the natural nerve, which is now a construction that still eats an n category, but produces now a marked simplicial set. And what is this construction? So I'm going to reuse as much as possible what I have already done. So the underlying simplicial set of the natural nerve of D will still be the previous nerve that was in a couple of pages ago, but I need to endow it with a marking. I need to tell you which simplices of this nerve are marked. And this is a definition. So I define that a K-simplex sigma in the nerve of D is going to be marked precisely when sigma is a K equivalence in D. Now, let's stare at this definition for a moment because it's short, but there is a lot that goes in it. First of all, let me remind you that maybe you don't remember, but I did point out that a K-simplex in the nerve of D consisted of a K cell with certain specified boundary conditions. And there is a definition for a K cell in D of whether or not it is an equivalence. If it is an equivalence, then I mark it in the nerve, and if not, I don't. And maybe you have never seen what is the definition of a K equivalence. It's not the most common thing. So let me just briefly elaborate on this. What is a K equivalence in D? This is something that is generally defined, or one way to define it is co-inductively. So this is the way I'm going to do it. I'm going to say that I take F from X to Y, a K cell. So X and Y in this case are K minus 1 cells. And I say that it is a K equivalence if I can find a K cell that points the opposite direction. So this is really trying to be some sort of inverse for F, but it's not strictly on the nose and inverse. The two composites are only equivalent to the correct identity. So such that, so, and K plus 1 equivalences that look like this. So I have G composite F that I would like to think is equal to the identity of G, but in this case, it's only equivalent via some eta. And F composite G is only equivalent to the identity of Y via some epsilon. So you see that there is some induction in this definition, because to understand when something is a K equivalence, I first need to know what is a K plus 1 equivalence. So it's maybe not the easiest definition, but this is what it is. And maybe it helps if I also say that if I take a very high dimension, being an equivalence just means being an identity. Then at the critical value, being an equivalence means being an isomorphism in the usual sense. And then in lower level, you need to use this co-inductive definition. So again, if this doesn't speak to you, for the purpose of the talk, I suggest that you pretend that K equivalence means K isomorphism. It's not completely correct mathematically, but it carries the correct moral meaning. Okay, so where are we? We decided that we want to work with marking, and I have declared that I want to consider a very specific marking on the street nerve, and this is called the natural nerve. Now, what can I say about it? I observe that this natural nerve that I just defined has a bunch of right lifting properties. And I am not going to define what each of those classes of maps are. They are a bit technical, and yeah, I don't think it would bring much insight since it would be too long for the purpose of the talk. But you can see that there is one that looks like a horn inclusion, but it has a marking on it. And then there are 3 different other classes. Instead, I want to tell you what is the property or the structure that is present in D that causes the fact that the natural nerve of D has the right lifting property. So the right lifting property with respect to the first class of maps is a symptom of the fact that in D, I have a composition law for morphisms. The fact that I have the right lifting property with respect to the second class of maps is a symptom of the fact that in D, if I compose 2 equivalences, I obtain an equivalence. This is also true for isomorphisms, I guess. So composite of equivalence is equivalence. The third one comes from the fact that equivalences and also isomorphisms satisfy the 2 out of 6 property. So equivalences satisfy 2 out of 6. And the last one comes from the fact that all cells in dimension higher than n are identities. So it doesn't matter that you remember exactly what is this list. Maybe what is more important is to remember that now that we have this marking, the structure of the natural nerve of D, both the simplicial structure and the marking, is able to capture structure and properties that are present in D. And this was something that was not achievable without the marking. Questions? Okay, so I wanted to, like originally, I was gonna state this fact as a theorem conjecture in the sense that we do this for the case n equals 2, and we believed it was true for the general case. But there is a really nice paper by Louboutin that came out a couple of days ago that seems to settle the whole general case. So in this case, this would just become completely a theorem. Okay, so with a lot of struggle, we have identified some interesting right lifting properties that the natural nerve of a category has, and we now want to use this to define what is an infinity n categories, infinity n category, kind of copying what we did for infinity 0 and infinity 1. So no, actually here I had left some space because I thought that we might have been lost at this point, and so I just wanted to write kind of a recap. So a recap is no, okay, I don't want to say it. So let me go here. So this theorem that I just stated is equivalently rephrased by saying that if X is isomorphic to the natural nerve of an N category, then X has the right lifting property with respect to the class gamma, by which I'm denoting just the class of all such maps. And one natural question that may come up is that in the previous two cases, we actually had a uniqueness of right lifting property here. There is no statement that is as neat as the one that we saw before. But what I think is true, without having looked into the details, but what I think is true is that X has the unique right lifting property with respect to gamma if and only if X is isomorphic to the natural nerve of D, where D is now a rigid N category. Being rigid means not having any not having any equivalence. But in any case, this doesn't matter too much. We have identified good properties for the nerve that kind of do all that we expect. And so we are now ready to define that X is an infinity N category if and only if X has the right lifting property with respect to the class gamma. And in the technical terminology, we say that X is an n-complicial set. So this is the main definition. It's hidden as a kind of a remark, but this is the main definition. We wanted to define what a n-complicial set was, and this is what it is. It's a simplicial set with marking that has a bunch of right lifting properties. If you look in the literature, there are many variants of things called complicial sets, and the reason is that those classes of maps were kind of discovered and used at different points and for different purposes. So there are different combinations of these classes of maps that you could consider, and objects that have the right lifting property with respect to those different combinations often are called something like complicial set. So if I wanted to be completely precise, I would say in this case that X is a saturated n-trivial weak complicial set, which is obviously too long, and therefore we shorten it in this way. Okay, so recap, what is an n-complicial set? An n-complicial set is a simplicial set with marking in which I should have the following interpretation. Case simplices should be thought as case cells with specified boundary conditions, and the case simplices that are marked should be thought of as precisely those case cells that are equivalencies, that are invertible in some sense. Okay, so we have identified something that satisfies us for the definition of an infinity N category. But I said I also wanted a model structure, and there is a supporting model structure for this. And this model structure is based on an extensive work by Dominic Verity, and then was somehow partially revised by Emily Reel, and then we have written down the missing details in our paper with Victoria. So there is a model structure on the category of mark-simplicial sets. And if I need it in the future, I will refer to these as mark-simplicial set infinity n. And what can we say about this model structure? We could say a lot, but for now, I will just say that the cofibrations are precisely the monomorphisms, and a monomorphism of marked simplicial sets is precisely a monomorphism on the underlying simplicial set. So this is something very easily checkable, and everything is cofibrant. And the fibrant objects are precisely n-complicial sets. So this suggests that my plan is now to take as M precisely this model category. Okay, but who says that this model category, this model structure is the good one? Like, I came up with something, but do I have any supporting evidence that it does the job? And here are two things that I hope will convince you that it's a good choice. So who says that it's the right one? One fact is a theorem conjecture. So theorem for n smaller or equal than 2 and conjecture for higher values, is that if I look at the natural nerve that takes an n category and produces a marked simplicial set, this defines a homotopical embedding. So it's a homotopical functor that sends equivalences of n categories to weak equivalences of marked simplicial sets. And it's an embedding. So what do I mean by this? So first, I have that two n categories are equivalent if and only if their nerves are. So the natural nerve is capable of recognizing correctly equivalences of n categories. And also, if I look at mapping spaces, then it doesn't matter if I compute this mapping space in n categories or in marked simplicial sets. And if you are a model category person, maybe this formulation looks somehow weird. The more technical and precise formulation of this that we have is as a right Quillen functor that is moreover a Quillen reflection or correflection. I don't remember which one of the two. But to phrase it in this way, I would have to work with a slightly less pleasant definition of this category. So if you allow yourself to work with a slightly different variant of marked simplicial set, then you can say that this natural nerve is a right Quillen functor that is moreover a homotopical embedding. Okay, so maybe this is one nice way to say that our theory of marked simplicial sets is recovering in a very good sense the theory of strict n categories. And the second supporting evidence is something that for the case n equals 2 has been proven, but with a lot of work, combining the work by many different groups of mathematicians. So it involves work by Bergman and Resk, but also Lurie, and very recently the last contribution by Gagna, Harpas, and Lanari. So if we combine a lot of things present in the literature, then we do know that the homotopy theory of the model structure of n-complicial set that we just built is equivalent to the homotopy theory of theta n spaces built by Resk. So I'm not going into defining or describing what theta n spaces are. If you know them and you recognize them, I think that the statement will make you happy. If you don't know what they are, you can just take for granted that this is an alternative recognized established model for infinity n categories. And so for n equals 2, it has been proven that they define the same homotopy theory. It has not been proven yet that this is true for higher n, but I think it's believed broadly. Yeah. Okay. So I hope that this convinces you that that the model structure is good. And whenever you work with different models of higher categories, you always, like, often there is not a perfect one, otherwise all the others would just disappear. A more common situation is that each model is gonna offer you some advantages and some disadvantages, and you need to take the whole package. So what I think is the best advantage of working with the category of Marx-simplicial sets is that compared to other models, you can do the theory of all n at once. So as you see, I gave you a class of 4 maps, and this allows you to define what is an n-complicial set for every n. Obviously, it will be a bit harder when n is 70,000 rather than if n is 7, but conceptually, the formalism is the same. Whereas if you work with other models, for instance, with the theta n spaces, the amount of data that you need to specify an infinity n category grows with n. So it would be very hard to give an infinity 70,000 category. But I also need to pay the price for something when I work with Marx-simplicial sets. As I said, there are advantages and disadvantages. And maybe one thing that is instead particularly complicated in Marx-simplicial sets is what I want to explore a little bit in the second part of the talk. And I want to describe what are some of the efforts that Victoria and I and also other people are doing towards trying to maybe correct those flaws or make them more manageable. Okay, so I would like to talk about small models of strict n categories. What is the situation where we are now? We have a vague idea of what is an n-complicial set, and we have a way to regard every strict n category as an n-complicial set by taking the natural nerve. And we also can consider, because the model structure allows us to do so, the mapping spaces out of such nerves. So this was something that we wanted, and we have it. Now the formalism allows us to define them and use them. The problem is that if we stare at those guys enough, we will realize that they are not they're not very manageable. They are complicated objects on the nose to work with. And let me try and explain why so. So one first useful remark is that, like for simplicial sets, when you work with simplicial sets with marking, everything is going to be a colimit of representables. And so you can use this colimit expression as an indication of how complicated an object is. Because if a simplicial set is a colimit of very, very many, infinitely many non-degenerate simplices, it's going to be a more complicated object than something that has only finitely many non-degenerate simplices, for instance. So in particular, if some A is a nasty, huge, infinite colimit of representables, then one of the effects is that when I look at categories of the, spaces of diagrams, this is going to be a nasty limit. So that's one thing. And then we are like, okay, but maybe when A is the natural nerve of a strict category, it's not going to be too bad. And unfortunately, this is not the case. So the natural nerve of a strict category is always less good than you would hope. And here's supporting evidence for this claim. So you can prove that the natural nerve of the smallest interesting two category that you could think of, so the category that has just one single walking two cell, is not finite by any mean. What do I mean by this? I mean that it has two non-degenerate simplices in each dimension. This is something that should surprise us because it's not true when we work with one categories. If you start with a one category that is very small, like finite number of pieces to build it, then the nerve is only going to have finitely many non-degenerate simplices. Whereas here we have infinitely many, two in each dimension. So you can imagine that when you look at the natural nerve of a more complicated two category than this one, things are not going to get better. So what you should remember from this is that nerves of n categories are essentially never finite simplicial sets. And again, in this specific case, the consequence is going to be that, or a consequence is going to be that when I map out of this guy, what I obtain is that this is a subset of an infinite limit. This is not good because this space is meant to be the space of two cells in my infinity two category X. So this means that if I want to name a single two cell in X, I need to specify an infinite amount of data. This sounds terrible and very painful. Therefore, we are after theorems of the following form. On the one side, something that is interesting, but not manageable. And we would like to find the representative, we would like to prove that this thing that is interesting but not manageable is equivalent to something finite or at least smaller. Because the more we can simplify this indexing shape, the more we can simplify the space of diagrams indexed over this specific shape. And so this is an example which is again a theorem conjecture. Let's look at the nerve of Cn, and I'm calling by Cn the free n cell. So for instance, what I was drawing here is the free two cell, the walking two cell. So this guy is way bigger than we would hope. So it's not finite. However, we can prove that it's equivalent to something super finite. There it is. So you take an n simplex, and then you look at one of the copies of the n-1 simplex that live inside it, and you kill it. So this is super finite because it essentially consists just of an n simplex. So if we want to explore what the green consequence would be for this statement, it would say that if now I want to look at the mapping space that defines the space of n cells in X, this is equivalent to a pullback of the set of n simplices of X over X minus 1 with X0. So now it's super finite. Now if I want to name one n cell in X, I just need to give you one n simplex of X that satisfies a certain condition, much less scarier situation. And let me draw a cartoon of what is the smallest instance of this and why it's overall an intuitive result. on this side, we have the nerve of the two cells. And on this side, what we are doing is we are taking a 2 simplex. So this would be delta 2. We are taking a 2 simplex, and then we are taking a copy of delta 1 that lives in it. And now I don't remember if it's the first or the second one. Let's say it's this one. And I kill it. I make it degenerate. So the way that I would draw this now would be this one. So we recognize that this picture and this picture are not all that different. So something that morally is not really counterintuitive. If you want to formalize it, this is hard. So it's really hard to prove this precisely. And the main reason why it's hard is that we start with something finite, and we need to build a sequence of anodyne extensions that eventually produce something non-finite. So this is achieved with a very complicated filtration that actually consists of several nested filtrations. And the way that we prove this theorem is in a more general setup. And this is the way it looks. So this theorem is a special case of the following. If you start with an n category, then you can do two things. On the one side, you can take the nerve of the suspension of D, and I'm gonna comment in a moment on what is the suspension of D. Or you can take the suspension of the nerve of D. And again, I'm going to comment in a moment on what the suspension of a simplicial set is. And this should be in n-1 category, the shift. Okay, so you could do these two things. It doesn't matter too much what these two constructions are. The point is there are meaningful and somehow existing established construction, and the theorem asserts that the nerve commutes with the suspension. And it recovers the statement over here when you plug in D being a cell. So let me just briefly say what these two suspensions are. And I believe that Victoria in her talk will give you details on what goes into this theorem and explore better the combinatorial aspects that are behind it. Okay, so if D is an n category, sorry, I have a bit of confusion with the shifts. So if D is an n-1 category, then the suspension of D is an n category. And what does it consist of? I will draw a cartoon for it. It has two objects, just two. And I need to tell you what are the Hom n-1 categories between these points. And each of the two objects as maps from it to itself has only the identity. So I will not draw anything. To go from the first one to the second one, I have D, which is an n-1 category, so type checks. And I have nothing to go back. So if you've never seen it, I don't expect you to digest it in 1 second. But if you have already seen it, maybe you recognize it. And instead, what is the suspension of a Marx-simplicial set? So if X is a Marx-simplicial set, the suspension of X is a push out of what? It's a push out of X joined with a point where I look at the copy of X that lives inside it and I kill it. Questions? Okay.
There were some questions in the chat, but I think Victoria is taking care of them.
Okay. Ah, good. Thank you. Okay. So this is one theorem that we prove, and there is another one that kind of has a similar story, but I don't want to go into any detail of it, so even less than the detail that I gave you for this one. I just want to give an idea of what the type of theorem says. And again, I'm gonna first give you the more concrete example. So let's stare at these two categories. This is a two category that has 3 objects and 1 and 2 morphisms generated by the things that I drew. And the theorem says that essentially you can split, you can cut at this point. So the nerve of these two categories is equivalent to the nerve of the first globe glued with the category of the second globe over a point. So if you were a theta n space expert, not only should this statement not surprise you, but if at all, you should be surprised that this is a theorem, because if you work with that other model, this property is built in. It's really part of the definition. But instead, when you work with n-complicial sets, even something like this that may look obvious, it needs a proof, and the proof is not easy. So how does this generalize? So it generalizes as follows. I don't want to be too precise, but if you have 2 n categories, A and B, and here, by the way, we don't have the theorem conjecture situation. This one, we have proven it for all dimensions. If you take A and B, 2 n categories that both have a special point, in the example from before, the special point was obviously this point. If we want it to be a bit more precise, this point has to be a cosieve in A and a sieve in B. But I think what you should keep in mind for now is just that in A, nothing comes out of this point, and in B, nothing goes into this point. So this suggests that there is a kind of flow that goes in that direction. So if you are in this situation, then if you're trying to compute the nerve of the category obtained by gluing A and B, so this is an n category that in particular contains all compositions of stuff in A with stuff in B, then you can realize it as the nerve of A glued with the nerve of B. And this is much smaller because all the stuff that exists as a composite of something in A and something in B are not present in the right-hand side. So this one is larger and this one is smaller. Okay, so these are some of the directions that we care about. We want to try and simplify representative of interesting things. But just to conclude, I want to mention one cool application that you can get if you put together the 2 theorems that I have just mentioned, namely this one and the one with the suspension. So, and this is something that we are writing up right now that is also joined with Julie Bergner, and we have it for n=2. I have mentioned that the theory of marked simplicial sets we know that it's equivalent to the theory of theta n spaces for n equals 2. But I said that to achieve this statement, one needs to go through a lot of work by a lot of different people. And in practical terms, this means that you can build a zigzag of Quillen equivalence, but there are many Quillen equivalences involved in them, and they don't all point in the same direction, and not all of them are super explicit. So what we had so far was somehow a not super constructive situation. Whereas if we use the analysis that we have discussed during the talk, then you can build a direct Quillen equivalence between the two models for n equals 2. And it goes as follows. We have theta 2 spaces on one side. And again, I will say a few things that will only speak to you if you know a bit of what theta n spaces are. I'm trying to define a left Quillen functor that takes a theta n space and produces a Martin-Pichel set. To do so, since theta n spaces are a category of presheaves, it's enough to define what it does on representables. And what does a representable theta n space look like? It looks like some two category like this. So this is a somewhat generic representable theta n space. And if I want to define what L does on this guy, it means that I'm looking for a candidate for a marked simplicial set that eats a two category. And since I've been talking about it for 1 hour, maybe we can guess that what I'm going to put here is the natural nerve of the same two category. So this is going to define a left Quillen functor. And if you put together the theorems that I mentioned before, you can achieve with a bit of work that it's a left Quillen functor. And then knowing that the two model structures have the same homotopy theory, we can also prove that this left Quillen functor that we construct is indeed a Quillen equivalence, relying on the existing work. Okay, yeah, that's what I wanted to say, and I'm ready for questions if Victoria has not taken everything already.
Thank you, Martina, for your talk. Any questions?
Thank you.
Are there questions?
Yes, I will ask maybe another naive questions. So you have n categories, you go to infinite categories, then infinite 1, infinite 2, infinite 3, etc. Can you move on this series of ordinals like this? Does it have some meaning?
I'm not sure I understand what you mean.
Okay, but maybe that's not because you mentioned you can define some like infinite, 70,000 category, right?
Mm-hmm.
So what about infinity, infinity, for example? Does it have some meaning or?
You can do it, and there is something in that direction, but that's another critical jump in difficulty.
Okay.
So
yeah.
there, as I understand it, there are at least two meanings that you can give to infinity, infinity, and those two ways are not expected to be equivalent. So you can do it. So it could be just something that has cells in every dimension and they are meant to compose, but you still expect them to compose weakly. And it is a bit, yeah, it's more complicated. Like there are even what I would call the guiding principle, there is a choice to be made there that leads to two a priori non-equivalent.
Okay, because the following natural question to ask would be, could you define the notion of alpha category for any ordinal alpha? Of course, with a critical jump in each limit ordinal. Maybe I'm not so clear, but
But like the infinite they are trying to put there is enumerating the dimension of the cells. So
okay.
I'm not sure what it would mean if you plugged in a different type of
Okay.
yeah, so I'm
Sorry,
not sure.
maybe that's just abstract nonsense, but anyway.
I'm also not super familiar with ordinals and cardinals, so maybe someone else has something to add, but
Okay, thank you.
There's a question in the chat. Can you read it, Martina, or shall I read it for you?
no, I see it. Does the complicial model structure satisfy the Barbour-Chomopris axiom of infinity n categories? So for n equals 2, yes, but if we knew that it satisfied them for general n, then we would also know that it's equivalent to theta n spaces, because theta n spaces do satisfy the axioms. So I think it is conjectured that that it will, but proving that it satisfies the axioms is somehow equivalent to proving that it's equivalent to theta n spaces, kind of. And at the moment it's open. Is your model of infinity n categories constructed from Szyszewski theory? Yes, I think you can. Victoria, can you confirm this? But I think you can.
So I think there's, to both questions, there's a technicality in there. Namely, there's a subtle difference of models of complicial space, or complicial sets, which we have hidden so far. Namely, so to satisfy Barwick-Chomopris axioms, strictly speaking, you need to be a pre-sheaf category, which is not the case for the category Martina presented, but something we have proven also is that you can modify it slightly, really tiny bit, so that you do get a pre-sheaf category, which satisfies for n equals to the Barwick-Chomopris axioms. And then you can also construct it from Szyszewski theory. In the case of Marx-complicial sets, and Martina has presented them so far, this is a Szyszewski all-shock theory, sorry. So yes.
So any more questions?
I have a small question about the markings. When you put n equals to 1, then you know there is an equivalence between your marked model and the usual Reschke model. And so in the usual Reschke model, you somehow get the model structure by inverting the nerve of an isomorphism. Is there some way to somehow recover your markings in an intrinsic way from the nerve of the isomorphism?
I mean, the marking when n equals 1, you will be marking isomorphisms. So yeah, I'm not.
And if you go further, if you go to n equals 2.
I had thought about it at some point, but I don't remember now what I had concluded. I would say it's hard or not obvious. Yeah, no, I don't have anything good to answer to this question. So I don't know.
Because in the model structure of Dimitri Ara for theta2 spaces, there is something which replaces somehow the nerve of the isomorphism. But you have a two-step somehow.
You mean
you have a two-step interval which has to be inverted, and so perhaps there is some relationship between your set of markings and these intervals. I don't know.
I mean, if you want to recover the marked two simplices, I think you should map out of the nerve of an oriental where the two cells that inhabit it is an isomorphism.
Okay.
I'm not sure if this completely addresses what you're saying, but it is some analogy, like it's something that represents the marking in dimension 2. Yeah,
Okay,
sorry.
thanks.
More questions? So in this case, Martina, thank you again for this nice talk.